Okay, so this video, after the video of properties of ring homomorphisms, we are going to check a couple of theorems. We begin with this one about kernels. Kernels are ideals. Let phi be a homomorphism from a ring R to a ring S, then the kernel phi, that's the set R elements in the ring R, where phi of R equals 0. So the kernel of phi is an ideal of the ring R. So we have a ring here, another ring here, S, and all elements here, that if you take the image into S you get 0. This will be the kernel of this homomorphism phi. Okay, let phi be a homomorphism. Okay, so the kernel of phi, meaning the set of objects that will be taken to 0 here. So kernel of phi is an ideal of the ring R. Okay, we get directly into the first isomorphism theorem for rings. Let phi be a... My phi today is really bad. Okay, this is a bit better now. Let phi be a ring homomorphism from a ring R to a ring S. Then the mapping from the ring division ring kernel of phi to the image of the ring through phi, so phi of the ring, given by R plus the kernel of phi into phi of R, it's the same element here. This is an isomorphism. Okay, usually we write it this way: the division ring kernel of phi is isomorphic to phi of the ring. I will do these isomorphism theorems in a second in a different way, but basically what we are saying here is that the image of phi is isomorphic to the quotient ring, right? The quotient ring of ring by the kernel of phi. Okay, that's all what this means. So the quotient ring of the ring by the kernel of phi to the image of the image of phi, if it is given this way, okay, they are isomorphic. Okay, so the last one is the last for the moment, of course. Ideals are kernels. Every ideal of a ring R, so we have a ring R, and here we have an ideal. So every ideal of a ring R is the kernel of a ring homomorphism of R. So in particular, an ideal A is the kernel of the mapping that takes from well, not easy to draw here. Imagine the same ring and we have an ideal A here. So an ideal A is the kernel of the mapping from the ring into the quotient ring by the ideal. Okay, I hope this is not too confusing. I will get back to this. But the very basic idea is really simple, right? Ideals are kernels. Okay, going quickly back to the first isomorphism theorem. I prefer to write it this way. So we are going to take phi. Phi is a ring homomorphism, so taking from a ring R to a ring S. 1. The kernel of phi is an ideal of the ring R. Okay, so the kernel will be the elements that we'll take into element 0, right? Okay, so all the kernel here, the set of all elements that will be mapped to 0, this is an ideal of the ring R. Okay, so checked. 2. The image of phi is a subring of S. This means that phi of R, this is a subring of S. Okay, phi of R is a subring of S here. The image of phi is isomorphic to the quotient ring R by kernel of phi. So R by kernel of phi is isomorphic to the image of the ring. Okay. In particular, if phi is surjective, so onto, then S is isomorphic to the quotient ring. I don't know if you can see the difference here. This is a particular case. Okay, here the third point that is checked already is the image of phi. So the image of phi is isomorphic to the quotient ring. It's isomorphic only to the quotient ring. Okay. Now, but if your ring of homomorphism, if your phi is surjective onto, then S. So if phi is surjective, the image will be all S, or will have the same structure as S. So then S is isomorphic. This S here will be isomorphic to the quotient ring. Okay, I hope you clearly see the difference here.